This is Facility Science Podcast number 7. I am Jason Doolittle, and today I'm talking about refrigerant. And so let's jump right into it. So a refrigerant is a substance, or sometimes a mixture of substances, that is used in a refrigerant cycle to move heat from one place to another. And a substance that we use as a refrigerant has certain properties that make it suitable for this use, which I'll get into later. And just as sort of a disambiguation, while there are multiple classes of substance that might be considered a refrigerant under certain circumstances, here I'm specifically talking about a refrigerant cycle in which the refrigerant undergoes a phase change to facilitate the heat transfer, and which I'll clarify what that means later on also. And this type of refrigerant and refrigerant cycle is widely used for cooling and heating and air conditioning, cold storage, refrigeration and freezers, and also dehumidification. So first, to sort of motivate this, imagine that you have a building in a very cold place covered with ice and snow, and inside the building you have, say, a workshop that creates some unbearable amount of heat. And you would like to take advantage of the fact that it's cold outside to cool down your workshop. One way you could do this is by taking some tubing, a hose, and running it all around inside your building, and then extending it, running it outside, and coiling it all up in the ice and snow so that you have a long loop of hose that's half inside and half outside. You could then hook up a pump and put some water in the hose and pump the water through the hose. And so when the water is in the part of the hose that's inside, it'll heat up, it'll pick up heat from your workshop. And then when the hot water reaches the part of the hose that's outside, it will cool off in the snow. And since relative to the heat that can be generated inside, there's effectively infinity amount of cold outside, the temperature inside will cool down, right? Eventually, you run enough water through here, the cold water will take a bunch of heat out of your workshop, and you're not going to heat up the outside very much because there's a lot more cold outside than there is hot inside. And so what you're doing here is you're using the water inside the hose to transport the heat outside. Now, the problem with the story I just told you is that in real life, when we want to make the inside of something colder, right, or move a heat out of something like a building or a refrigerator, it's usually hotter on the outside than on the inside, right? So we want to make the refrigerator colder than the room it's in, but we have to move the heat from inside the refrigerator into the room where it's warmer than we want the refrigerator to be. So in this case, the idea of pumping the water through the hose to move the heat from a hot place to a cold place isn't going to do the trick, because we want to move the heat from a cold place to a hot place. So instead we use what's called a refrigerant cycle, which requires refrigerant combined with some energy in the form of a mechanical work to move the heat from the cold place to the hot place. So how does this work? Well, based on the story I told before, we really want a magical kind of substance that's colder than the air inside. So say inside the refrigerator, so the inside air can heat it up. But then somehow it's hotter than the air outside so that the outside air can cool it down. And unfortunately, no such substance exists. So we have to be clever. And before I tell you how clever we are, I want to cover 3 thermodynamics concepts, so a little bit of thermodynamics background. So the first one is called latent heat. In this context, latent heat is the heat required for a phase change, say from a liquid to a vapor or a gas. I'm going to use, just a side note here, I'm going to use both vapor and gas kind of interchangeably. They're technically slightly different things, but the difference doesn't really matter here. So like I said, I'll probably just use them interchangeably. I'll use water as an example to describe latent heat. So if you add heat to water, the temperature of the water will increase up to the boiling point. And once the water reaches its boiling point, it will start to boil, which means it's changing phase from liquid to gas. It's turning into steam. And if you were able to capture all the steam, sort of hypothetically, so that none of the heat is able to escape from the mixture of water and steam, and you continue to add heat to the water-steam mixture, the temperature wouldn't continue to increase. The temperature would stay the same until all the liquid water had turned to steam. And then when you had only steam and no more water, then the temperature of the steam would start to increase as long as you kept putting heat into it. So that extra heat that goes into the phase change, but that doesn't increase the temperature, that's called latent heat. And then if you go the other way, if you remove the heat from the steam, the same thing happens. The temperature of the steam will decrease until you hit that condensation temperature, which is the same as the boiling point, the temperature where the steam turns into liquid water. And at that condensation temperature, continuing to remove energy from the steam won't cause the temperature to decrease anymore, but instead will cause the phase change. And then once all the water is liquid, continued removal of heat will start to decrease the temperature again. Right? So, and then related to this concept of latent heat is, so the name for the heat that results in a change in temperature, you call that sensible heat. So sensible heat results in a change in temperature, and latent heat doesn't. Instead, it results in the phase change. It's the heat of the phase change. All right, the next thermodynamic concept is that the boiling point, or the condensing point, same thing. The boiling point of a substance depends on pressure. So you might know that water boils at 100 degrees Celsius or 212 degrees Fahrenheit, if you're into that. You might also know that that's really only true at sea level or at 1 atmosphere of pressure. And if you ever lived at a high altitude, you might know that water boils at a lower temperature at a high altitude. And that's because there's less pressure from the atmosphere holding the water vapor down in the container. And the basic idea of this, if you can control the pressure being exerted on a substance, you can alter the boiling point of that substance. All right, now the third thermodynamics concept is that under controlled circumstances, if you increase the pressure of a gas or liquid, that will result in an increase in the temperature of that gas or liquid. And if you decrease the pressure of a gas or liquid, that will result in a decrease in temperature of the gas or liquid. So those are the three thermodynamics concepts. Now let's get into the refrigerant cycle. And for simplicity, I'm going to describe the refrigerant cycle as if I'm talking about a typical air conditioning scenario where we want to cool the inside and put the heat outside. In general, in this scenario, it's hotter outside than it is inside. So there's 4 components in the refrigerant cycle: the compressor, the condenser, some type of expansion or metering device, and the evaporator. And since the cycle is a closed loop, there's no real starting point. The refrigerant just goes around and around the loop. So we can just start at an arbitrary place. So we'll call step 1 is where the refrigerant as a vapor or gas enters the compressor. And the compressor compresses the gaseous refrigerant, increasing its pressure, and consequently, by the thermodynamics concept I covered before, its temperature. So increasing its pressure increases its temperature. So now our refrigerant is a hot, high-pressure gas, because it was a cooler gas, and the compressor compressed it, and which caused it to heat up and be at a higher pressure. Now, step 2 is that the hot, high-pressure gas enters the condenser, and the system is designed to set up so that by traveling through the condenser, the refrigerant will change from a hot, high-pressure gas to a hot, high-pressure liquid. In other words, the refrigerant will condense in the condenser. That's why we call it a condenser. So the condenser removes the latent heat from the refrigerant, and then any additional heat that might have gone into increasing the temperature above the boiling point. So in the typical air conditioning scenario, the condenser is outside, and the refrigerant has been heated by compression to be much hotter than the air outside. The condenser, sort of mechanically, is a coil of copper pipe arranged to maximize the surface area, and then a fan that blows the outside air, across that coil. And since the air is cooler than the refrigerant by design, the air removes heat from the refrigerant and just takes it away. And while air-cooled condensers are typical, using water to cool the condenser is also fairly common. Now, step 3 in the cycle is now the hot, high-pressure liquid that just came out of the condenser, hits the metering device, an expansion valve. There's several different types of this. And that presents a resistance to the flow of the refrigerant. So in the simplest case, you can think of this as just a spring-loaded valve. Actually, in the simplest case, it's just a small hole that the refrigerant has to force its way through. But I think it's easier to think of it as a spring-loaded valve. And the refrigerant sort of has to force its way through the expansion valves, which means there will be a lower pressure refrigerant on the other side of the metering device. And this drop in pressure across the expansion device causes a decrease in temperature. So in the section of the loop beyond the expansion device, we have a cold liquid now. So it went from a hot liquid after the condenser to a cold liquid when it passed through the expansion device, which caused the pressure to drop. And more likely, it's actually a mixture of cold liquid and vapor. So basically, the refrigerant is sort of near the boiling point at its new temperature. Now, step 4 is that this cold liquid enters the evaporator. And while traveling through the evaporator, the refrigerant heats up and, surprise, surprise, it evaporates. That's why we call it the evaporator. So in this step, the refrigerant takes on the latent heat of vaporization and then possibly heats up a little bit beyond that, past the boiling point. And the cool vapor leaves the evaporator and continues toward the compressor to restart the cycle. And again, in the typical air conditioning situation, the evaporator is a coil of copper tubing and a fan that blows air across the copper tubing, just like the condenser. In this case, the coil of copper tubing is inside the building. And so heat from the air inside the building is transferred to the refrigerant. And the system is designed so that the refrigerant in the evaporator will end up being much colder than the inside air so that it can take on the heat from the inside air and boil and evaporate and then take that heat away back to the compressor. So that's the cycle, 4 steps. Now, a couple notes about the compression step and the expansion step. So in the compression step at the compressor, we do work on the refrigerant to increase its pressure. We're putting energy in, and that's actually the majority of the energy consumed in the form of electricity is usually in the compression step. So we're putting energy in there to increase the pressure. And then in the expansion step, so that's the metering device, the expansion valve, the refrigerant then does work on the metering device to decrease its pressure. It's having to force its way through, for example, by pushing against a spring. And ideally, the energy added to the refrigerant by the compressor and the energy removed from the refrigerant by the expansion valve are roughly equivalent, which means that the heat removed from the refrigerant in the condenser is equivalent to the heat added to the refrigerant by the evaporator, ideally. Never really ideal, but that's the ideal concept. So the compression step and the expansion step, they undo each other. They're simply there to change the boiling point of the refrigerant to suit our needs by manipulating the pressure of the refrigerant. All right, now there's 2 more related terms here that I want to cover, and those are superheat and subcool. So the refrigerant absorbs heat when it travels through the evaporator. And the main function of the evaporator is to convert the refrigerant from a liquid to a gas while taking on the heat. And the heat that causes the conversion, the latent heat, doesn't increase the temperature of the refrigerant, like I said before. That's what latent heat is. Now, any additional heat the refrigerant picks up beyond the latent heat will increase the temperature of the refrigerant vapor, and the temperature increase above the boiling point, so above the latent heat, we call that superheat, and it's measured in degrees. So if the refrigerant leaves the evaporator at a temperature that's 10 degrees above the boiling point, we say that there's 10 degrees of superheat. And some amount of superheat is desirable. It ensures that no liquid refrigerant will enter the compressor. Liquid refrigerant in the compressor is bad. And the wrong amount of superheat indicates a problem with the system. And so the proper amount of superheat depends on the exact parameters and design of the system. Now, the other term, subcool, is very similar to superheat, except that it references the heat removed from the refrigerant in the condenser. So in the condenser, heat's removed from the refrigerant, and the latent heat is removed during the phase change from a gas to a liquid. any removal of heat beyond the latent heat goes to reducing the temperature of the liquid refrigerant. And this is called subcooling. And like superheat, subcool is measured in degrees. So if the refrigerant leaves the condenser 10 degrees colder than the condensing temperature, we say there's 10 degrees of subcool. And just like with superheat, there's a right amount of subcool for any system. Okay, now I want to talk about manifold gauges. You've probably seen these things, you might wonder what they're about. There's these gauges with hose hanging off of them that your HVAC mechanic is always carrying around. And these are one of the primary tools used by refrigeration service personnel. And these allow measurement of refrigerant pressure in the refrigerant loop. And normally there are two different places to connect the gauges to the system by the hoses that are hanging off. And the two places are what they call the suction line. And that's the section of tubing that's between the evaporator and the compressor. So in this section, the refrigerant is a low pressure gas. And the pressure is relatively low here because the compressor is pushing gas from this section into the high pressure condenser section. And it's called the suction line because the low pressure pulls or sucks refrigerant through the evaporator. And then the other connection point that's typical is what's called the liquid line. And this is the section between the condenser and the metering device, so the expansion valve or whatever. And in this section, the refrigerant is a warm liquid. So that's why it's called the liquid line, because the refrigerant is liquid here. And so in a closed system of fixed volume, which is what our typical refrigerant loop is, it's a closed system and the volume is fixed. The pressure and the temperature of a substance are directly related. So in other words, if you know one, so you know the pressure, for example, you'll also know the temperature. If you know one, you know the other. And so the pressure gauges will tell the technician the temperature of the refrigerant as well as the pressure. In fact, usually both things are written on the gauge. So the needle on the gauge will point to a pressure, and it'll also have the temperature written right under that. And the information provided by the gauges, along with other supporting observations, allows the technician to determine if, for example, there's enough refrigerant in the system, or maybe there's too much, or if there's the right amount of heat exchange in the evaporator or in the condenser. Or it tells them a lot of things, again, with supporting observations that allows them to diagnose various problems with refrigerant loop. All right, now, typical refrigeration system, like I've been describing, can only create so much of a temperature difference between the evaporator and the condenser. And when the temperature gets too great, the temperature difference gets too great, the pressure differential that you have to manage becomes unmanageable. And some industrial processes or scientific or medical applications require evaporator temperatures that are much colder than a typical refrigerant cycle can manage. And the solution in this case is to use multiple refrigeration stages. So depending on the required temperature, this can mean adding an additional compressor along with some other gas and liquid management mechanisms in the loop, or it can mean using multiple separate refrigeration loops. So in the case of multiple loops, what that basically means is you would have one loop cool the refrigerant in a second loop, and then the second loop cools the space that you're trying to cool. And this can be nested several stages deep, where you have a one loop cooling a refrigerant in another loop, and you sort of cascade it down till you have the coldest loop, then cooling the space you need to be really cold. And this cycle, this refrigeration cycle, we typically use it to cool things down, but we can also use it to heat things up. We can reverse it, basically. We can put the condenser in the place that we want to heat up and use the same exact cycle. And we call this a heat pump, usually. So you could say that the refrigeration cycle is equivalent to the heat pump cycle. Same thing, we're just moving heat. And many systems are designed to actually be reversible. So they have a mechanism in the refrigerant loop to reverse the flow of the refrigerant so that what was the evaporator becomes the condenser, and the condenser becomes the evaporator. Okay, now let's talk about some types of refrigerants and regulations that are related to refrigerants. Okay, now that we know how this refrigeration cycle works, we can decide, so what are the desirable properties of a refrigerant? So first of all, it has some desirable thermodynamic properties. So for example, a high heat of vaporization. So that's the latent heat associated with the liquid to gas phase change. We want a good amount of heat required to make that phase change. And then we also need a boiling point in the desired temperature range. We need the refrigerant to boil in the evaporator and to condense in the condenser. So we need a substance that can be made to do that at reasonable pressures, at pressures that we can manage inside our copper tubing and with our compressors, and not too much of a difference between the two. And so those are our desirable thermodynamic properties. We also want the refrigerant not to be corrosive to the system components, so the copper tubing and the compressor materials and the seal materials, because we're going to have this refrigerant, sitting inside this machine for potentially 10 or 20 years maybe. And so we want to make sure that isn't a substance that's going to deteriorate those systems over time. Ideally, the substance would be non-flammable, although some substances used as refrigerants or proposed to be used are flammable, but ideally they wouldn't be, because basically you might end up creating a bomb. And then also you want it to be not harmful to the environment. If possible, there have been concerns about the environmental effects of some refrigerants, leading to regulation of these substances. The primary environmental effects are ozone layer depletion and global warming potential or climate change potential. So there are many types of substances used as refrigerant, and refrigerant types are often referred to using an R notation. So this is an R followed by some numbers and possibly some letters. And originally, in the original system, the numbers referred to the structure of the refrigerant molecules. So the numbers would indicate the number of carbon and hydrogen and fluorine atoms, while the letters would indicate the particular atom arrangements or possibly some other added elements. And that R system has since been expanded to include other refrigerants that don't conform to the coding system. For example, a blends of different substances. And some examples that you might have heard of are R12, R22, R134A, or R410A. Those are some very common ones, although there's probably hundreds of different types of refrigerant that are named in this R notation. But basically, the right type of refrigerant to use in a particular piece of equipment is the refrigerant that it was designed for. And as I kind of mentioned before, some substances used as refrigerant have been determined to have unreasonably high environmental impact, resulting in regulation of these substances, notably CFC and HCFC refrigerants. So that's CFC is chlorofluorocarbons and HCFC is hydrochlorofluorocarbons. So refrigerants that are these types of substances that are widely used as refrigerants have been almost completely phased out of production in many countries, largely due to their negative effects on the ozone layer. And this phase out was initiated by what's called the Montreal Protocol, and that's an international treaty that was initially agreed to in 1987. An example of an extremely common HCFC refrigerant you might have heard of is R22, commonly known by the name brand Freon 22. And this refrigerant and others like it are still used in a lot of equipment all over the world, although the use of refrigerant has been increasingly restricted since the Montreal Protocol. So if you've been involved in facility management or engineering in the past 20 years or so, you've probably had to deal with R22 equipment and deciding whether it's time to replace it or whether you can continue to service it. And we're coming really close to where using R22 or any kind of CFC or HCFC refrigerant equipment is going to be completely unreasonable in a lot of the world. And so I have in front of me here a document called the EPA's Updated Refrigerant Management Requirements. And for those might be listening that aren't in the U.S., the EPA is the U.S. Environmental Protection Agency. And the subtitle of this document is called What Supermarkets and Property and Facility Managers Need to Know. And this goes over kind of an overview of what we're supposed to do with our refrigerant using equipment that's these refrigerants that are regulated now under the Montreal Protocol. And so it says here, Section 608 of the Clean Air Act prohibits the knowing release of refrigerant during the maintenance, service, repair, or disposal of air conditioning and refrigeration equipment. The EPA requires proper refrigerant management practices by owners and operators of refrigeration and air conditioning systems, technicians, and others. And so this, you can read this document. It's linked in the notes for this episode here. All right, so there's this part of this document here that's called How Will the New Requirements Affect Supermarkets and Property and Facility Managers? And it summarizes, basically, it talks about which types of appliances are affected. So appliances that contain 50 pounds or more of one of these ODS, ozone depleting substances. It talks about calculating leak rate whenever we add refrigerant to a piece of equipment like this. Because the only time you would need to add refrigerant to an equipment that's not, a retrofit or an installation, or maybe a seasonal variance of changing the refrigerant charge, is if some refrigerant had leaked out. So we need to calculate the leak rate when we add new refrigerant. We have to keep track of how often we add refrigerant and how much we add, so that we can know over time how much is leaking. And then it talks about what are the acceptable leak rates for the different types of equipment, and that we have to document the leak rate test and follow up after repairs. And if we can't repair the equipment, the rules say that we have to create and implement a retrofit or retirement plan, replace the equipment basically, or convert it to another type of refrigerant or whatever. And it also talks about record keeping and reporting. So owners, operators must maintain hard or electronic copies of records documenting the full charge of appliances, records such as invoices showing when service or maintenance is performed, when refrigerant is added to an appliance, when a leak inspection is performed, and when a verification test is conducted. It also talks about if using an automatic leak detection system, documentation that the system is installed and calibrated must be recorded. Documentation of retrofit and retirement plans has to be kept. Records to demonstrate if we're adding refrigerant or removing refrigerant for a seasonal variance. Reports on appliances that leak 125% or more of the full charge in a calendar year. Basically, they're telling us that we have to manage devices with these refrigerants in them and make plans to replace them if they leak refrigerant too much. And if eventually, we're going to get to a point where you can't get the refrigerants anyway. So if you have equipment that's still using these types of refrigerants, you should definitely be thinking about retiring that equipment and getting it replaced with newer equipment that uses refrigerants that don't have these problems with them. Okay, so that's about all I have to say about this topic for now. My notes for this are at facilityscience.com/podcast, and this is number 7. So if you have questions about this topic or any comments or suggestions for topics, you can reach me by email at podcast@facilityscience.com. I'd love to hear your feedback. So I hope this is helpful to you, and thanks for listening.